So this is the second of two videos that are meant to replace a missing lecture for one reason or another. In the first video, we talked about very briefly what we mean by the ray aspect of light, the fact that we're going to be drawing lots of pictures where light is just an arrow, and that's because that's really how we can treat light coming from a distant source. And then our previous video focused on the law of refraction, also known as Snell's law, where when light goes from one material to another, air to glass, water to air, any of those sorts of boundaries, it changes speed and wavelength and actually bends relative to the perpendicular. Our goal for this video is to get into a little more details of what else can happen when we have light trying to have refraction. A little bit more of the details, mostly concept-based, but not all. And for this video, we're going to be covering sections 25.4 and 25.5. We're still not going to be at the heart of chapter 25, which is figuring out how to determine where an image forms when light passes through a lens or light bounces off of a mirror. That's going to be in class when we have a chance to be talking about the concepts and doing things on the board the way that we normally do. This is just a supplementary video to catch up on time that we've lost. Okay, so reminders of what we talked about in the previous of this pair of videos. We introduced the idea of Snell's law, which happens when light goes from one medium to another. We learned that this dashed line that we keep drawing, as long as we're drawing these pictures, is called the normal line because of that mathematical definition of normal meaning perpendicular. And then the letter N that shows up in Snell's law and in the image here on our slide is the index of refraction, and that index of refraction is based on the material that light is moving through. In a vacuum, it is by definition 1.0 with as many zeros as you can possibly draw. In air, it is close enough to 1 with enough zeros that we're always going to be rounding it to 1 in our class. For water, N is 1.33. It's basically 1 1/3. And then for other materials, it's larger than that typically. For glass, it tends to vary somewhere between 1.5 and 1.7. And the textbook has tables of different values that might show up. So here's another example that we are going to sort of try as a, right now, that makes us realize that something happens if our angles get too large. Okay, so our goal is to shine light from water towards air and find the expected angle of refraction. Okay, so I'm gonna sort of take us out of this and have us think through what's going on. Okay, so we have, for Snell's law, we're starting in water. And so for N, that's 1.333, and it's the sine of 50 degrees. And we're going towards air, which is 1.00, and our goal is to find the sine of that angle, so of theta 2. Okay, now the tricky thing is that when you solve for the thing on the left here, we end up with 1.02, and 1 times the sine of theta is just the sine of theta. And if you try, let's go back to the big screen. If you try to take the arc sine, or the inverse sine of 1.02, your calculator is going to get very mad at you. It's not possible. It's undefined. So something happens. Our math wasn't bad, right? We plugged in the numbers we were given. Something happens if we go from a higher index of refraction material into a lower index of refraction material, and only if the angle gets too big. That weird something that happens is called total internal reflection. So look at this example here. This is a enclosure filled halfway with water, and we have different light sources. One that shines basically straight up, and if we have something shining straight up, it doesn't really bend. We have one at a shallow angle, it bends a little bit. We have another one at a bigger angle compared to the normal, and it refracts at a bigger angle. And if we go too far, there is no refraction. All of that light bounces off the surface, and we're going to be talking more about reflection itself and the law of reflection in the next time that you have class. But when refraction can't occur and it stays within that higher index of refraction medium, that is called total internal reflection. Okay, so the limiting case on this is whatever the specific angle is where the refracted angle would be 90 degrees, the sort of maximum value that we can have without going back into the medium. And because we're at that maximum critical angle, we'll have reflection instead. So we want to draw this out. And then if we're starting in water, we have 1.33 times the sine of this angle we're looking for equals 1.00 times the sine of 90 degrees. The sine of 90 degrees is just 1. And so the thing we're plugging into our calculator, and if you need to write it out on your sheets, then just pause the video and catch up. That's the beauty of a recording. The sine of the angle we're looking for is 1 over 1.33, because it's 1 times 1, and then we divide both sides by 1.33. And the angle itself would be the inverse sine of that. So again, we'll sort of pause this. We'll plug in numbers right here, messing up all the slides. So we get 1.33 times the sine of this angle critical that we're looking for. And this is 1 times sine of 90 degrees. And so the sine of that angle, if we divide both sides by 1.33, is 1 divided by 1.333. We can solve for the angle itself, and the angle would be 48.6 degrees or 49 degrees. And that's what that would look like. Okay, so the critical angle, the way that we solve for it is we basically set the refracting angle on the other side to 90 degrees. And since the sine of 90 degrees is just 1, we can simplify Snell's law for this particular case to look like this, where N2, as it always is the later medium that we're trying to go into and don't manage to, and N1 is where we start. So I want you to try to calculate the critical angle for light going from glass with an index of 1.5 into air at 1.0. I'm not going to do this math for us. It's just kind of making sure that we can use that arcsine function on our calculator and recognize what numbers go where. Since we're starting in glass, that's N1. We end in air, or we're trying to, that's N2. And so when you calculate this, you should end up with an angle less than 45 degrees, if not something went wrong in your calculation. Okay. So one application of these ideas has to do with this nice, simple triangular prism. Now, the next couple of slides are pretty much all based on critical thinking of these concepts, and we're not trying to just default to plugging in numbers. So for this first question, if we go straight at this glass, what should the angle be when it goes from air to glass? So relative to the normal, what should the refracted angle be? Pause the video if you need to think about it, but basically try to think in your head, what's the arrow going to look like if it makes it from air to glass? Okay. Hopefully we haven't lost our understanding of windows, right? If we look straight through from air to glass, there will be no bending of any kind because the sine of 0 is 0 degrees and we don't bend away from that normal. However, when it hits the far side of the glass, in the previous slide, hopefully you did that calculation just to check that you're following along, but I said before in that 2 slides ago that for glass, the angle is going to be less than 45 degrees. So when we come over and we hit this coming sideways, what is our angle between the normal and that incoming ray for that glass to air boundary? Is it more or less than the critical angle? And if it's at the critical angle, that's still going to be total internal reflection. And so based on your thought for part A, what's going to happen to that light then? Is it going to refract and end up on the opposite side in the air, or is it going to total internal reflect? So pause the video if you don't have an answer yet and think about it. Okay. So we get total internal reflection because 45 degrees or more is enough to have it bounce within the glass itself. And when it hits the bottom of the glass, what angle is it going to leave when it goes from glass to air? So another concept question for us. Pause the video and think about it. Okay. It goes straight out again because the angle relative to the normal was 0 and the sine of 0 is 0 degrees. So we had no deflection because we're going straight through. We had total internal reflection because we hit that 45 or more degree threshold. And then we had going straight through with no deflection because we went straight at that boundary. This prism, this shape, is called a right angle reflector. It's used in a lot of engineering purposes. And if you put two of them together, or you make something that is this shape, you can just have light bend back out again and come out the way it came in, while not actually having any kind of solid wall for it to bounce off of. It's actually just bouncing because of that total internal reflection. It's all air on the outside of this, and yet it doesn't shine through that glass. Kind of cool. One of the applications of this total internal reflection that you might have seen, that you might have used before without realizing what's happening, is that binoculars are one of the simplest ways of having this happen. They have these total internal reflectors basically bounce the light back out in order to have you go around with a sort of spyglass like a pirate, although who wouldn't want to look like a pirate, right? But the point is, there are these internal prisms that the whole goal is just to make that path length smaller so that you're not going around with a giant spyglass, although you might want to choose that instead. Other more important in many ways applications are fiber optics. So not just light, but any other wave signal, electromagnetic wave signal, so radio waves or anything else, can be sent along a fiber optic tube that is made of basically material like glass that if we let that signal bounce off at the right kinds of angles, we get to keep all of that signal. It doesn't leak out by refracting out. It's kind of stuck in the tube. That's used for a lot of different things. So fiber optics, some people have internet that uses fiber optics. I sadly don't. I need to upgrade at some point. But a lot of different applications are basically in order to allow signal to carry through. Other things, it's just to get light from one place to another. So if you ever had one of those cool lamps that had a whole bunch of little lit up dots, just because it was shining light at the bottom of each of those little plastic things. There's a lot of applications, including in medicine, where sometimes we need to be able to observe within a patient where everything's dark, there's no light source. And this allows us to shine light down to show where we need to go, even if it has to bend around in a lot of different ways, because it's basically held within that fiber optic cable. So, kind of cool. Okay, so our second of our two separate topics for today, the next section in the chapter is dispersion. Now, dispersion is something that we're going to talk about almost exclusively as a concept question. So when we had the example of the two-step refraction problem, back when the first video that we had of the two, and we have a class handout that you can refer back to, we actually gave a different index of refraction for red light because red light and blue light all have different indexes of refraction within a given medium. So what happens when you shine light through a prism is not actually the nice simple lines that we've been drawing. That's only true if you're looking at one wavelength. But if you're looking at sunlight, for example, or a light bulb and a incandescent light bulb, when you shine that light through the prism, each of the different wavelengths bends a little bit differently because it has a different index of refraction, and you end up with a wavelength or a rainbow on the other side because of all those different wavelengths. This is called dispersion. So sending white light through a prism and having it break up into those different colors is because it's dispersing. Now, a real photo instead of a diagram, it's the same idea. You shine light through and you get a rainbow on the other side. It's one of the ways that Isaac Newton studied light was by shining sunlight through a prism and having it break up into a rainbow. And the really interesting thing is this is something that will happen slightly differently depending on what the prism is made out of. So crown glass, acrylic, fused quartz, each have these different changes in index of refraction. If it was a single straight line at a given number value, then it wouldn't cause this dispersion, and so the sort of steeper that is, the more of a rainbow you'll have. One of the most well-known popular culture examples of this is the Pink Floyd record cover for Dark Side of the Moon. The left one is the most iconic, where you have that dispersion, but the 2001 reissue added a little bit of physics where there's some reflection off that very first surface, and that's going to be a real phenomenon as well, is there's always going to be a little bit of reflection that comes off for the angles that weren't quite right, and then the rest of the light shines through and makes that rainbow. Now, one of the other really cool aspects of dispersion is rainbows. Okay, so probably all of us have seen a rainbow in real life, and almost certainly all of us have seen a rainbow of one form or another in photos. But you may not have thought all that hard about the requirements that you need to have to see rainbows. So if we're in Grand Rapids and we want to look to see a rainbow, can we face any compass direction? I want you to think about that. So you can pause the video and think about it if you want to. And then for this particular diagram that we have here on the right, what is that blue circle trying to indicate for us? It's the thing that sunlight is refracting, then total internal reflecting, and then refracting back through. But what is that representing? Okay, so pause and think. All right. So for the first question, part A, you can't actually see a rainbow at any compass direction you want to because you need to have the sun behind you. And in the northern hemisphere, including Grand Rapids. The sun rises in the general east direction, sometimes northeast, sometimes southeast. It goes high in the southern sky, and then it sets in the general west direction, northwest, west, or southwest, depending on the time of year. But that means that you have to face mostly north in order to see a rainbow. If you are facing south, the rainbow will not be in your field of view, but you might be looking northeast or northwest, depending on the time of day and time of year. And then the blue circle here is indicating or trying to simplify model of a raindrop. In order to have a rainbow, you have to have rain. So if you've ever seen a rainbow, it's really important to recognize that you're seeing that rainbow because there is sunlight behind you and there is still water droplets in the air. Either it is just after a really heavy rain or it's going to be raining more soon, but the sunlight has to be out, so it's not overcast. And that sunlight is shining through all of those different droplets, and they're all going through that refraction, total internal reflection, and refraction again. And based on where you're standing, you'll see a rainbow for the angles between 40 degrees and 42 degrees from basically directly sideways. The angles in this photo are super exaggerated, but it really helps us understand a little bit about why we're seeing red high up and blue low down. If you ever draw it, that's how it looks. And it's worth recognizing that it's because the highest intensity red that you're going to be seeing is higher up, and the highest intensity of what's aligned with your eyeballs lower down is going to be the violet. So for either of these people, that's what we're keeping in mind, and that's now we've got the little rainbow drawn for us. But there's a couple more details that we want to think about, right? How about a double rainbow all the way across the sky? That happens when there's two internal reflections, and so you get the red and blue opposite of what it's supposed to be, right? Look at the left side of the screen. We see that red's highest and blue is lowest. For the double rainbow, we're actually going to get the opposite. And so what we end up with is that secondary rainbow. The red is closest to the red, and the blue is furthest away, kind of on both outer edges. So we include a picture of a rainbow over Isaac Newton's house, because he was the first to really think about sunlight being made up of multiple colors. But any double rainbow that you see, the secondary one that looks upside down is always going to be fainter. And it technically is always there available, but usually too faint to see. There's not enough of that double reflection, double internal reflection. Now, a couple of last notes about rainbows that you might not have thought too hard about, but it's worth mentioning. We're simplifying things with that 40 degrees, 42 degrees. Even if we just think about red, it's not all at 42 degrees. There's kind of a range. And if we look at each one of those wavelengths, things look a lot more complicated. That's the zoom in here. And a separate note, something you may not have ever noticed, but the next time that you see a rainbow, hopefully you will, is when you look at the rainbow itself, there's also a lot of scattered white light below the rainbow and not very much above it. And that again comes from the more nuanced, complicated stuff happening within those drops of water that we're not going to get too far into. But that's something that's worth recognizing, is that it's lighter below the rainbow than it is above it because of additional scattered rainbow light at those lower angles. So there you go. This video covered total internal reflection, and it covered dispersion, both of which are primarily concepts, and that's why we haven't stopped to do very many practice problems. And this is a standalone video that you should have watched after the Snell's Law video. The next time that you're in class, you'll be continuing chapter 25, thinking more about mirrors and reflection, and then moving on to how lenses and mirrors actually can create images for us, real and imaginary.